Hello friends, so today we are just going to complete the next part of our third chapter, that is equilibrium diagrams. So up till this lecture we have seen about the cooling curves and whatever may be the Gibbs phase rule, how we can be able to apply the Gibbs phase rule for the different kind of that cooling curves. So those cooling curves are very much important because whatever may be the cooling curves are there, based on that cooling curves, the further portion of plotting of equilibrium diagrams that we are going to cover in this particular lecture. Now, what is the importance of plotting of equilibrium diagram and how it is going to plot, or which kind of the techniques that has been used to plot the equilibrium diagrams that we are going to cover in this particular lecture. So friends, just to plot the equilibrium diagram, first of all, you just consider about what is the equilibrium diagram. So equilibrium diagram can be plotted by using these several techniques such as a thermal analysis, dilatometry, optical and electron microscopy, X-ray and electron diffractions. So thermodynamic data analysis, it is required electrical resistivity and magnetic measurements. So these are the various methods just to plot the equilibrium diagrams. So each method has a certain advantages and limitations. So basically these techniques are there. You just understood these different techniques. Through these different techniques we can be able to plot the equilibrium diagrams. But how the equilibrium diagrams are going to be plotted, this is very much important. So most of the times the equilibriums or phase diagrams are plotted by the method of thermal analysis using the data obtained from cooling curves. So this is the very much important technique. So generally here we are just going to cover through the thermal analysis, we are obtaining the data through the various cooling curves, and those thermal analysis, that method of thermal analysis, through that method of thermal analysis, we are going to plot the equilibrium diagrams. So other methods are generally used to eliminate the ambiguities existing in the diagram plotted by the above method. So ambiguities in the sense whatever may be the some sort of that minor doubts are there. So that ambiguities, just to eliminate those ambiguities through the thermal analysis, the remaining methods, that is the electron microscopy, X-ray, electron diffractions, thermodynamic, that electric resistivity. So those are the different kind of that methods are used just to eliminate some sort of that ambiguities. So generally the basic method of plotting the diagrams are through the cooling curves. This is explained by the one sample which is mentioned over here. So let us consider a binary copper nickel system. So copper and nickel have 100% solubility in the liquid and solid state. So these are the two elements that binary system we have taken, that is the copper and nickel, and both the copper and nickel are 100% soluble in liquid as well as in the solid state. So these following steps are required just to complete. So take the one example. This is the copper, percentage of nickel. So the percentage of copper will be varying from 100 to 0 and nickel will be varying from 0 to 100. So this is the first material in which 100% copper is there. There is no any nickel alloy is present. So it means that the material number 1 is pure metal, which is made up of just only with the copper. Now after adding the 10% of nickel in it, the composition will be like that. That is the 90% copper will be there and 10% nickel will be there, and this will be nominated as a material number 2. So likewise for material number 3, it will be 80%, it will be 20%. So we are just going to add a nickel percentage in it. Now again, in the material number 11, the 0% copper and 100% nickel. Again, it will be a pure metal which is made up with the just only the nickel. There is no any percentage of copper is present in this. So likewise, this is the one sample we have taken for our equilibrium diagram. So now the next step here, these are the cooling curves we have drawn for the that 11 materials. So here that material number 1, material number 2, material number 3, material number 4. Likewise, this will be the phase material number 9, 10 and 11. So here you just go through that cooling curves again, that lecture of cooling curves. So here we can be able to just plotting the cooling curve, that is the temperature versus time. Okay, so this is one part of cooling curve, that is the temperature versus time. So cooling curves for pure metal and solid solutions alloy. So for the cooling curve of pure metal, so for the material number 1, here for the material number 1, 100% copper is there, 0% nickel. So this is the pure material or pure metal, and for the pure metal, the phases will be changes from liquid to liquid number 1. One in the sense here just solidification will be started. So it will be started at the just constant temperature. So this will be a horizontal line, and again the solidification will be started at S1 point and it will be a pure solid. And this is for the alloy. So it will be a slanted edge for the alloy. So we have drawn all this. Again for the last material, material number 11, it will be again the 0% copper and 100% nickel. So again here we have to draw the cooling curve of pure metal. So L to L11, 11 in the sense that material number 11. So that nomenclature is given likewise, and then this will be a curve. Now here all those L1, L2, L3, L4, what we have obtained in this cooling curve. So basically the liquidus and solidus temperatures of these materials, the liquidus temperatures are marked as L1, L2. So this L1, L2 are the liquidus temperature. Okay. And S1, S2, S3, S4, again S5, 6, 7, 8, 9, 10, 11. So these are the solidus temperature. So again we can be able to join these points also. Okay. So from S1, or here we can say S0 to S11, we have to join all those. Okay. So this will be the cooling curve. Okay, that is again the solidus temperature we have explained, that is S1 to S11, and since the material 1 and 11 are the pure metals, they solidified at a constant temperature, and hence their liquidus and solidus temperature are same, that is L1 is equal to S1 here, that L1 is equal to S1, and at the end L11 is equal to S11. So the temperature will be same. So transfer these temperatures to the temperature versus composition graph as shown in next figure. So here all those has been shown over here, and these two lines, that L1, L2, L3, here we have joined. Okay, and again that S1, S2, S3, S4 we have joined over here. So this is the percentage of copper, percentage of nickel over here. Okay, so sorry, this will be the temperature and this will be a percentage of nickel we are adding over here. Now for the first metal, the whatever may be the temperature, it will be shown 1083 degrees Celsius, and at the nickel it will be 1453 degree Celsius. So this will be here we are just have to draw a smooth curve from point L1 to L11 and from S1 to S11. So which represents the liquidus and solidus of the diagram. Now above liquidus temperatures are all the material are in the liquid state, and below the solidus temperature, okay, all the material above the liquidus stage, all whatever may be the material it is there, it will be in the liquid state, and below the solidus curve, whatever may be the material it is there, it will be in the solid state. So this will be everything will be a solid below this line, and above this line everything will be in the liquid state. Okay, and whatever may be the in between it is there, that is the liquidius and solidius temperature, the alloy are in the liquid plus solid state. So in between this, whatever may be the alloy it is there, it will be in the both the state, that is liquid as well as solid. So this will be a phase of liquid plus solid. So this is the equilibrium diagram. Okay. So at the temperature such as T, the average composition of the existing liquid is given by the point X. So here, whatever may the point X you can be able to see, this will be an average composition of existing liquid, and the average composition of the existing solid is given by the point Y. So average temperature or existing solid, that is indicated, that composition it is indicated at the point Y. So X to Y, this will be a line. So here I think it has been clear to you. Now we will just go further with some sort of the prediction phase. These are the rules for the different things. So one example of bismuth and SB that we will explain in the next lecture. Now this is the lever arm principle. Now lever arm principle. What is the lever arm principle? That we will just see in this particular lecture, and then again for the different alloy, how that cooling curve is varying for the bismuth and SB, that we will see in the next lecture also. So here first of all just try to understand what is the lever arm rule. So the lever rule is used for finding out the amount of phases existing in the binary systems. So whatever maybe the phases are there, so that lever rule, it is used to find out the amount of phases existing in the binary system for a given alloy at any temperature under the consideration. So at any temperature, which kind of that phase it is there, that has to be identified. So this diagram we have taken from the previous. So about this particular curve, so whatever may be the stage, it will be of that metal, that is of liquid, and below this particular curve, whatever may be the stage of that material, that all will be in the solid. So in between that, liquid plus solid. So the liquid phase that has been shown over here with the point C, that is for the liquidius, and for the solidus it will be shown by point D, and this will be a F, that is the liquid plus solid, whatever may the midway, or we cannot be able to say the midway, but whatever may be the curve it is there, there is that bisection, and this will be a percentage of that particular material B. So here two materials has been taken, material A. So this will be a melting point of metal A. This will be a melting point of metal B. Okay, so this will be a concentration weight of B. So material will be goes on increasing. Okay. Now what is the phases? Here we are just again explained over here. A and B are the two metals, so which is shown over here, A and B. So these are the two metals. Z is the composition of alloy under the consideration. So this will be a Z percentage, that alloy composition percentage. Then T is the temperature, which is shown over here, that is indicated by the nomination T. Then amount of solid S and amount of liquid is equal to L. So whatever the amount of solid, that has been indicated with S, amount of liquid, that has been indicated with L, and whatever may be the L it is there, that is nothing but the 1 minus S. Why it is 1 minus S? Because suppose we have taken the 100 or 1 quantity, so whatever may be the solid it is there, so liquid, how much is it will be a liquid? So 1 minus S. If suppose no solid it is there present, the no solid form, then total stage will be in the liquid. So L is equal to 1 in that case. So that's why it is indicated by 1 minus S. Now, how basically the lever arm principle is applied, that will be discussed in the further part. So just consider the amorphous system of two metals A and B. So already we have explained, and Z is, it is just a whatever may be the composition of the alloy under the consideration. Now we are knowing the amount of B in the alloy is equal to amount of B in the solid plus amount of B in the liquid. So whatever may be the total amount of B, it is there. So total amount of B in the sense that whatever may be the second metal. So the total amount of B in the alloy is equal to amount of B in the solid plus amount of B in the liquid. So suppose if it is present in pure liquid form, so amount of solid will be 0 and amount of liquid will be 100. If it is present totally in the solid form, in that case the liquidity is not present, that metal B which is not present in the liquid form, and the total whatever may be the material that alloy it is there, that will be present totally in the solid. Now Z is just composition. So Z is equal to S into D plus 1 minus S into C. So what is this D and C? Just understood that S into D in the sense, just consider this particular figure. So Z, that is, we are just going to calculate the composition. So composition is equal to solid into this particular point D, which is just a average, that percentage of that composition in that previous figure that we have seen by that X and Y. So average composition of existing solid, which is indicated by point D, and average that composition of existing liquid, which is shown by this point C. So S into D plus, we can say L into C initially. Here L into C, whatever may the composition we are going to calculate, S into D, L into C, liquid into this particular point C and solid into this particular point D. Okay, so this particular L, that is replaced by 1 minus S. You understood this? Which is very simple. Okay, so S into D plus L minus L into C. So this L is directly replaced by 1 minus S over here. Now we are just segregating those things. S into D, that is SD, plus we are just multiplied that this C under this bracket, so it will be S plus C minus SC. Okay, now this C we have taken into this particular side. Now this equation will be like this: Z minus C is equal to S, we have taken the common, and into bracket D minus C. Okay, now what is this S? Now we have to calculate this S. S is equal to Z minus C divided by D minus C. Okay, so that is, now this Z, here we can be able to say this Z is nothing but, the F. Okay, because basically here this will be on the same line. So here we can be able to replace this Z by F. So this Z is replaced over here by the F. Now the equation will be becomes S is equal to F minus C divided by D minus C. Okay, so this will be a solid state what we are getting. Now here just see what is this F minus C. F minus C, just go into this particular diagram. So F minus C in the sense this particular arm FC, when we are just minusing this particular point F minus C, what is remaining? This particular arm, so FC arm. Okay, so here that F minus C in the sense arm length CF or FC, anything you can be able to take. Now D minus C in the sense this arm length that is present, that is the CD arm. Okay, so this is the arm length CD. Okay, so this is for the solid. Now similarly for the liquid, we have to calculate, that is the amount of liquid L is equal to 1 minus S. Already we have taken over here 1 minus S. Now yes, we have calculated already. Okay, so that is nothing but the arm length CF divided by arm length CD. So arm CF divided by arm CD we have taken. So this S is replaced by this. Okay, that is CF upon CD. So here we are replacing CF upon CD. So L is equal to what? This arm CD, which is taken over here, okay, divided by arm, whatever may be the CD minus arm CF. So CD minus CF. What is the CD minus CF? CD minus CF. So what is the remaining? FD. So here we have taken that arm FD, because here just see 1 minus CF upon CD. So CD minus CF. So CD minus CF in the sense here we have explained CD minus CF. What is the remaining? FD. So that's why here taken arm length FD divided by arm length CD. So that dividing factor is remains. So therefore S upon L, when we are just dividing these two terms S upon L, so this CD and CD will be gets cancelled. What is remaining? Arm length CF and arm length FD. So arm CF divided by arm FD. So through this CFD, this will be a liquidous stage, this will be a solidus stage. So amount of solid into arm FD, okay, S into what will be there? Arm FD, and arm CF into L, that is liquid. Amount of liquid into arm CF. So this will be goes over here. So here S into this arm FD, L into this arm CF. Only we are just changing the terms. This is just simple mathematics. When this denominator factor will be goes to this side, it will be in the numerator. This denominator factor will be when it will be comes into this side, it will be in the again numerator. So S into arm FD, L into arm CF. So therefore, the amount of solid, what is that? Arm FD, that is nothing but its lever arm. For the solid, what is the lever arm? That is FD is the lever arm. So arm its lever arm. Similarly, for amount of liquid into its lever arm, or amount of liquid into arm CF in the sense, it is the lever arm for the liquid. Okay, so this is nothing but the lever rule. Okay, because at any temperature the amount of solid and liquid phase can be determined in its similar manner. So this will be a lever arm principle. So I hope you have just understood what is the lever arm principle through this lecture. Again we will just see the same phases for the different material in the next lecture. So thank you very much for patience listening.